Hello everyone, welcome back. So, in the last class we derived the LES equation for the incompressible flow, and we also looked at the properties of the filter, and in what case you basically I mean in how what are the ways in which these filter basically differ from the averaging process that we use in the Range equation. We saw is that in these filters. Okay. So, you can write phi equal to phi tilde plus phi prime, okay. And on the other hand, let us say if you want write phi equal to phi bar plus phi prime. So, in this case this is turbulence fluctuations, and this is your subgrid scale fluctuations. Okay. And we also saw that here in this case phi prime bar equal to 0, but here phi prime tilde is not equal to 0 because of the properties of the filter. Okay. And there are some other differences also. For example, if you apply the filter twice, it is not same as applying filter once. On the other hand, this is if you apply your averaging twice, it is equal to the average applying the averaging once. Okay. So, this is your Range and this is your LES. Okay. And by applying this filter, we derive the incompressible filtered Navier-Stokes equations, and where we saw that we had an extra term which was tau SGS, right, which needs to be modeled. But this is different from the tau eddy or tau turb that we had in the Range in a way that this only applies to the smallest grid that we have, okay, where we want the dissipation to happen. So, we are still resolving the spectrum up to great extent. After that, we just ask it to go down, and we are not resolving some region which are for the responsible for dissipation, right. Now, let us look at the compressible flow. So, when we go to the compressible flow, we have some differences. The first thing is that your density becomes also a variable. So, whatever operation that you are applying, whatever filter that you are using, density is not a constant. So, you have to have basically the rho tilde also. Okay. In the case of incompressible flow, density is a constant, right. So, in that particular case, if you apply this filter on rho, okay, this will be nothing but rho, okay, because of the properties of the LES filter, okay, the low pass filter. Okay. If it is applied on a constant, it will give you the constant back. Okay. This is not true for the compressible flow. Okay. And if you try doing it for your advective term in your compressible flow equation, in the momentum equation, okay, you will quickly realize like we had for the Range equation. Okay. So, you have basically rho tilde plus rho prime, u tilde plus u prime, v tilde plus b prime, okay, and you can apply this filtering operation entire thing, and you will have so many terms, right. Okay. I think you will have around 9 terms, 8 or 9 terms, okay, and this quickly makes the algebra too much cumbersome. And the way we got rid of this in our Range is that we used something called density weighted averaging, the Favre averaging. Okay. The same idea we are going to use in LES also, and without going into much detail, we are going to basically define an operation which is phi bar, which is nothing but your filtered rho phi divided by the filtered rho. Okay. So, your rho filtered phi bar is equal to rho phi tilde, right, and this phi can be u v. So, if it is rho tilde u bar, okay, is equal to rho u tilde. Okay. This idea is directly borrowed from the Range derivation of compressible equations for the compressible flows, right. because there is a typo here. So, if you do that for the continuity equation, what we will get is this will become d rho tilde by dt plus del by del xi, and you can write it as rho u tilde, but this can also be written as rho tilde ui, right, by this property. Okay, that will become rho tilde ui bar, right. So, this is your continuity equation. This is easy to derive, like we have done for the Rayleigh equations, and similar idea if you apply for the momentum equation. Okay. So, we want so we will have this rho u I u j tilde, right, and then you can basically take rho u I as one variable and the u j as another variable, and like we have done for the Rayleigh equations. If you do the those derivations, and plus you also write in terms of like rho u I u j, okay, is equal to like this rho u I u j plus rho u I u j tilde minus rho u I u j, right. If you do like this term can go to your SGS stress tau I j SGS, okay, and this term is what will come here, and rho u I tilde can be written as rho tilde u I bar, right. So, this is how you can derive your compressible filtered equations, okay. And similarly, I mean you can derive for the energy equations also, the idea remains the same. You can apply the filter, and wherever you have this multiplication of rho u, you take this there are 3 variables, you take this rho u together and another variable which may be E, or which is energy, or maybe enthalpy, okay, or even the velocity. You can apply this and you can derive this energy equations. So, this I leave to you, can go back and do this exercise as your homework, and you can derive your energy equation, write those terms one by one, and you can see that what is the energy equation that you are getting. Okay. Now, so far so good. Now, what we need to do now is basically find out tau I j S G S. Okay. What is my subgrid stress, okay, which is responsible for the dissipation of energy. Okay. You would in many literature you would see that this filtered equations are not derived, and you directly use the complete Navier-Stokes equations and plus this tau I j S G S term. You will not have this tilde and bar sign, and that is because in the implicitly filtered LES you are basically not applying any filter, okay, as we have been discussing for the last couple of classes, that in the implicitly filtered equation the grid acts as a filter. So, essentially you have the Navier-Stokes equations, you are solving for the variable which you can call as a resolved variable, okay, u, v, w, p, rho and so on and so forth, and you also add a subgrid stress tensor, okay, where the grid size is sufficiently small, right. So, that is what you are going to do, right. So, that is why this ui bar and rho tilde, these are not the average equations, okay, either Favre or Reynolds, okay, these are not average, these are the filtered quantities, it can be implicitly filtered or explicitly filtered, okay. So, that is a very important difference that you need to realize, despite of the fact that the form looks very similar, you should not be confused that we are now solving for the instantaneous flow variable, okay, which is basically how the signal is varying in time, and you still need to do the averaging while to calculate the average quantity, okay. You are not getting the average quantity directly in your LES, like we discussed couple of classes back, is that LES is first simulate and then average, okay, Rayleigh is first average and then simulate. So, that idea you should not forget, okay, and despite the similarity in the form between Rayleigh and LES, you should remember that in Rayleigh we are solving for the average Navier-Stokes equations, here we are solving for the filter Navier-Stokes equations, but this filter can be an implicit filter also, where we are basically not doing anything, we are just ensuring that the energy gets dissipated at the smallest grid size that is available to us. Okay. As long as we can ensure that the energy is dissipated and the build up is not happening, okay, we can basically run the simulation. Okay. Now, let us go to the SGS model. So, we have this subgrid stress tau ij SGS. Okay. How do you find the find this value? So, you need to have a model, right. This is a closed term and you need to have a model. Okay. So, let us go to the SGS model. Okay. So, again we will borrow the idea from the RANS model. So, remember, I mean, I am doing it for the compressible, the incompressible is even easy. Okay. So, this is Favre averaged. Okay. In incompressible, if you have tau ij r, that will just be written as 2 mu t S I j, okay, bar, right. This is what we had discussed, and that will be it can also written as rho nu t into 2 S I j bar. Okay. This terms comes here because we need to ensure that when you take the trace, it should give you the kinetic energy. So, this is for the Reynolds stress for the incompressible flow, and this is for the compressible flow. So, I am deriving for compressible, but I hope that you can make the connection, like what are the terms which are, I mean, so far it should have been it should be clear to you that what are the difference between compressible and incompressible flow. Okay. So, we will borrow this idea and apply in your LES SGS model. So, this is again the concept of eddy viscosity. So, you have many variables. So, tau SGS, if you write this, okay, it will have like 6 independent tensors, right. So, you will have 1 1, let me write in a proper way, okay, tau ij SGS, okay, tau 1 1 SGS, okay, tau 1 2 SGS, tau 1 3 SGS, and then this is tau 2 1, okay, tau 2 2, tau 2 3, tau 3 1, tau 3 2, tau 3 3. Okay. These are the SGS models, and then because this is symmetric. So, 1 2 is equal to 2 1 and 1 3 is equal to 3 1, but still we have 6 variables that we need to find out, right. And what we did in the eddy viscosity model is that we know that we have the strain rate tensor available, right. So, and we know that for the stress quantity, okay, the natural distortion of flow is related to the strain rate. So, why do not we make use of the strain rate here also? So, we can define this tau Sj SGS, okay, is proportional to basically your strain rate tensor, okay, and the proportionality constant, like for the fluid stress we have this nu, which is the natural viscosity or the molecular viscosity. In this case, it will be a nu SGS, okay, multiply by rho, right. So, this is what is eddy viscosity model is, that ISIJ is known from your simulation, okay, this is a strain rate tensor, and rho is known. So, the only unknown we have, or the only thing that we need to model is the nu SGS, which is your eddy viscosity, right. So, we had 6 unknowns and we basically simplified our problem to just one unknown, and that we need to find out. Okay. So, for the compressible flow, this will be your expression, okay. You have strain rate tensor and then your viscosity, and this 2 terms, I mean, it comes out because, I mean, if you write it for a simple shear flow, okay, let us say if you have a simple shear flow like this, and if you write your strain rate tensor, okay, so that will be right. So, del u I by del x j. Okay. So, half del u I by del x j plus del u j by del x I, right. So, here if you write this standard tensor for a simple shear flow, where the only variable you have is del u by del y, right. So, you will have two places where it will come as half. Okay. So, this is 0 half del u by del y 0 and then half del u by del y, all other terms will be 0, right. This is how it will look like. Okay. And then if you do Sij, okay, basically you do term to term multiplication. Okay. So, that will be half del u by del y square and plus half del u by del y square. Okay. And that will be nothing but and if you take the square root of that, okay, so you will have a 2 term coming here. Okay. 2 Sij star. Okay. So, that is how these 2 terms come here. Okay. Because there will be 1 by root 2 term coming here, and you can derive it and you can see that there will be a factor 2 coming in because of the consideration that you have this coming here also and here also. Okay. Now, just get back to the expression that we have. Okay. So, Sij the star, why we use star here? This is the old notation that we have been using for the range flows also, is because we have this 1 by 3 delta u k by delta x k, because for the compressible flow our del dot u is not equal to 0, right. So, that will come and you will have the consideration of the bulk viscosity in this particular case, and that is why we denote it as Sij star. Okay. The other reason why we are using Sij star here is that in some of the simulations, some of the codes, what they do, they absorb this term with the pressure, right. So, the pressure is also a normal stress, right. So, you will have pressure coming here, okay. All other components are 0 and this term is also acting normally, right. So, what you can do, you can absorb this term into the pressure, okay, and then you will have a modified pressure, and then all you need to basically use the SGS model applying only on this basically shear stresses. Okay. So, that is another way some of the SGS models or some of the eddy viscosity models are used, where they absorb this term into pressure, okay. That is just another way of doing things. Okay. Now, the question is, how do I find out the new SGS, right? That is our variable. Use the same idea that we had in RANS. The new SGS is, the unit of this is meter square per second, right. So, in order to get that, we need a length scale and you need a velocity scale. Okay. This is your meter and this is your meter per second. Okay. For the length scale, we will use the same idea that we had in RANS, that we had this integral length scale, right. So, if you are, and that was representative of the some of the geometry that we had. Similar idea can be used here. Okay. So, here we call it as a subgrid length scale, and because this model has to be made in such a way that it acts on a grid which is of a given size, right. So, that grid size has to come into the consideration. So, that is why you will have this CS multiplied by this volume to the 1/3. This is nothing by your delta, right. So, delta is a representation of your grid size, right. And as discussed earlier, this volume can, if it is structured grid, this is delta x, delta y, delta z to the power 1/3. Okay. And CS is a mechanistic constant. Okay. Its value is it can be determined by performing a DNA separately. So, what the value of this can be anything between 0 to 1, and different codes will have different values. For example, I think Fluent uses 0.1, some other codes use 0.17 and so on and so forth, right. But if you are developing a code for LES, and you want to find out what is the value of your CS, what you can do is you can perform your perform a DNS for your flow, okay, and then you perform an LES for your flow with different CS value, and you can see that for what CS value you have the best representation or best approximation to the DNS, and that is how you can determine your smegmacy constant. Okay, but it will be somewhere between 0.1, 0.2, 0.3 and so on and so forth, right. Now, we found our length scale, okay. We need to but I mean as we have done, if you remember our Prandtl mixing length model and Van Dist mixing length model, what we have discussed is that we have a log layer, right. So, if you plot this u plus versus y plus, okay, this is how it looks like in the log scale. Okay. So, this is somewhere your log layer, okay, and what we have derived is that your velocity changes as kappa y in this, okay, if you use the log scale. So, what it does this kappa y, it ensures that it is respecting the law of the wall when it comes close to the body, right. In all other regions you can use this CS delta to the power 1 by 3, but if it is a wall bounded flow you need to respect the how the velocity is satisfying the no slip condition when it comes very close to the wall, and that is why this kappa y comes into the picture, and you can take the minimum of this kappa y or this CS multiplied by delta. Okay. In fact, you can also use a correction of the Van Dist, okay, which also basically matches the value more accurately in the log law region, which is I think e to the power minus 1 minus y plus by a plus or something like that. Okay. So, we have discussed about this Van Dist model earlier, okay, and multiply by delta. Okay. So, this also ensure that this is your Van Dist model and then CS delta. So, minimum of these two. Okay. So, this will take care of your damping also very close to the wall, okay, e to the power 1 minus y plus by a plus. Okay. So, this is Van Dist mixing model. What did the correction on the Prandtl model. Okay. And you can refer to our earlier lectures, we have discussed about this mixing length model in more detail. Okay. Now, let us finalize our model. So, we got this length scale, okay, which I will just write here CS delta, okay, and what we need is the velocity scale, right, and because this mixing model is inspired by this mixing length model, okay, what happens in the mixing length model is that you basically look at the gradient, okay, and multiply by the, so this let us say this is your del u by del y and multiply by this length scale, that will give you the velocity scale, right. So, similar thing we will do here also. So, you will your del u by del y will be replaced by, for a general 3 dimensional case, 2 y Sij tilde Sij tilde, okay, and multiply by your length scale will be multiplied by delta, right. So, this is your length scale and this is your velocity scale, and if you multiply that, so nu t will be u naught L naught, it will become CS delta square root of 2 Sij tilde Sij tilde. Okay. So, this is your the SGS viscosity, okay, nu SGS. Okay. I should not write nu T, this is an error here, okay, this should be nu SGS, okay, because I have been using the same slide, I wrote it nu T, this is nu SGS. Okay. Now, this is the Smegmansky model, and the value of CS has been basically calculated by many researchers. There is Germano and there is Lilly, and Many of the researchers actually use this homogeneous isotropic turbulence to basically calculate CS, and different values have been proposed over the years. Okay, and as we discussed, it can go to 0.17, 0.1, 0.23 and so on and so forth. So, if you are using a code, you can go back and see what is the viscosity constant that you are using. Okay, last comment I want to make is on different models. Okay, like we have this. So, when you want to use this LES model, what happens when you go very close to the wall, it requires some modification, okay, because you have this viscous sublayer where the LES I mean the SGS viscosity is not very important, okay, and then you have the law of the wall. So, it all needs to be respected. Okay. So, in order to basically address these issues, we had these models. Okay, we have the Weyl model. Okay, what it does is basically it actually modifies the velocity scale, so that it can address the value how it approaches the wall. Okay. So, this modifies the velocity scale. Then of course, we have this Van Rist model, okay, which basically ensures that there is a damping in the viscosity when it approaches the wall. Okay. And then we have some kinetic energy based model, okay, TKE based model. What they do is that they change the equation itself when it approaches the wall. Okay. So, this is a very very important aspect, and that is why you have many models when it is a wall mounted flow. Okay. So, apart from this, you can have wall model LES, where it is a kind of hybrid model between the RANS and LES, okay, where you model the flow very close to the wall. You may use a RANS equation, okay, and away from it you can use a LES equation. There is wall resolved LES, where you are basically resolving everything, and then you have a Weyl model, we have TKE based kinetic energy based model, we have Van Rist model, and these are the different ways to basically handle the viscosity very close to the wall. Okay. So, this is what I had to discuss about this LES, and we have covered that how LES sequences are derived, what kind of filters that you can use, and even if you need a filter, and how do you use the viscosity to basically ensure that we have enough dissipation, so that the solution does not blow up. Okay. The only remaining thing that is that needs to be covered is that how do you ensure that turbulent fluctuations are given to the flow, right. So, what happens, like if it is a RAN simulation, what you do, you give a turbulence length scale or the turbulence intensity, and it calculates your K and epsilon, right. We discussed in the RANS classes. It is not so easy in LES. Okay. Let us say let us go to our example of flow over a turbine blade, let us say. Okay. So, let us say this is how our geometry is, okay, okay, and this is your inlet, okay, and there is certain turbulence level, let us say 5% is your turbulence level. So, you cannot give an integrated quantity, right. You cannot give let us say turbulence kinetic energy or the dissipation rate in the beginning. Okay. What you need to give your U prime, V prime, W prime, rho prime and P prime and so on so forth, right. You need to provide the fluctuations, right, in LES or a DNS, right. So, if I am an inlet turbulence coming in, you need to provide the fluctuations, right, and it is a very important thing in LES and DNS, because if you do not provide this, then what you are doing is essentially your incoming flow is laminar, okay, and I mean for it to develop turbulence, it will require a very long length, okay, and typically you cannot afford those kind of things. So, there are ways to basically provide your input turbulence. You can have a precursor simulation where you can find out these fluctuating quantities based on the turbulence level, or there are approaches like digital filter. Okay. There are approaches by Lund where you basically recycle and rescale. Okay. So, and the other thing is that it needs to be changing with time. So, it has to obey certain statistical property of a turbulence, and it should change in time. Every time you cannot have this like say fluctuations. So, it has to be basically correlated in time, it has to be correlated in space, right. So, that is another research area, that how do you provide your input turbulence for a LES and DNS simulation, and we will cover some of this aspect in future classes. Okay. So, with that we will stop here. Thank you very much.